non-repeating and randomly generated. Okay, what does that mean? For example, a non-repeating value could be the output of a counter, that is unlikely to repeat during the lifetime of the authentication key, comma, or a date and timestamp. So, we know that there's a clock inside each device. So, where do they take the seed from? Remember that we can't get the clock offset with a simple non-authenticated inquiry. What if someone reads the specification like I did and follows the specification? Actually, I didn't have time to actually measure the quality of the output, but I guess some implementation should be really fucked up, because what is a specification worth if it goes like, oh, random number generator, use randomize, generate random numbers, it's fine. No, it's not. So they don't trust it themselves, obviously. The reason for using the output of and not directly choosing a random number as the key is to avoid possible problems with degraded randomness due to a poor implementation of the random number generator. So they pipe it to E2 mode 2. But actually it doesn't it helps, but come on, it should be random. So introducing BTCrack, it was first presented at hack.lu. It's actually released right now, so you can find it on the website, you can download it now. It cracks the PIN and the link key. It requires the values from a pairing sniff. For convenience, you may import CVS data from your capture. Interesting thing, if you download it now, there's a hidden message inside the zip. The first person to find it will get the source code. So just do as the message indicates if you have wireless. I don't think many have, but if you have, download it and do as the message says, and I'll give you the source code afterwards. Obviously, we'll release a Linux port with the source code afterwards, but you'll get it now. So the history. Ollie Whitehouse, 2003, he presented the weakness of the pairing process and how it may be used to crack the PIN. He didn't implement it, he presented it. Shake and Rule actually implemented and optimized the attack. They found ways also to reinitiate pairing, which is the key point, because to crack the key, you have to sniff on the pairing process. And the pairing process actually just happens once in a while. But if you can actually reinitiate the pairing, you can capture it live. So you say that you can actually the implications of the attack are a lot bigger if you have a way to reinitiate the pairing. So it felt quite awkward to actually write my name there. There was tremendous help from somebody that will recognize himself. It's the Windows 32 implementation, first public release. Oops. So just to give you a few numbers, version 03 did 22,000 keys per second, 05 did 47,000 keys per second. That's actually just because I implemented threading, and because it's dual core. And then, thanks to Eric Sesterhan, we actually optimized the whole logic for caching. He cleaned up the mess, he used static functs, he removed the junk, and he compiled with ACC, which gave this, which is quite the difference. You see that. Clean coding does help. So we have a 4-digit PIN pretty much in real time. 4-digit PIN in, well, it's not real time, but pretty close. So Windows XP recommends 8 digits. And well, I haven't measured here, but it's around 11 minutes. So unless you change the PIN. Okay, can you come after the talk? So I'll give you. So somebody reads the license agreement. So just come after the talk, come see me. You'll get. I'll either give it immediately or send it over email. Where was I? Yeah, Windows recommends 8-digit pins. So unless you change the key, the link key every 10 minutes, you're not really secure. Oops. I think Apple, what does Apple? Also 8. 6, 8, something around the line, but it doesn't help really because it's digits only and they don't use UTF-8, so it doesn't really matter. It's pretty much broken. That's the logic of the pairing process. You generate a random number. Yeah, I'll go through it pretty fast. In the middle is actually the value that we can sniff. And if you go through all the logic, you'll see that everything, the thing that is left out is actually the pin. The pin is the shared secret between the device A and the device B. So, yeah, obviously pin length, we can get the pin length, because if you have the pin, we have the pin length, obviously. So there's just one thing, and it has a very low entropy. So here's the logic of Shake-Then-Wool. And here's pseudocode from Thomas Rybicki, published in Hacking 9 in 2005. And it pretty much shows everything. You calculate the hypothesis for K-init, which is here. You decode LK round and LK round B, which is here. You calculate the hypothesis for Ka, which is here. You calculate SRAS out of our round, which is here, and you compare it. If SRAS is SRAS, we have the key. If not, we'll start over and we'll increment the pin. And we go over and over again until SRAS A equals SRAS. So let's demo this, and I hope that thing won't crash, because the driver is pretty fucked up, and if you connect the USB cable and you retract it and you reconnect, it blue screens. And that's actually one new feature of their new version. Let's just to mention it, that software that costs over $10,000. One feature of their new version is the driver is more stable. So let's see if this works out. That's quite a benchmark now, because all these interferences. We'll see if it works out. I will actually synchronize to the master, which is this, this device. It has a few options to synchronize. Synchronizing in Bluetooth terms is getting the frequency right, knowing where to hop next. So we'll start and see if it works out. Here at the bottom we see BPA waiting for frequency hopping sequence. Oh, there it is. It's synchronized. So now I'll try to pair up with that vulnerable version here. So, oh, sorry, I forgot. Somebody give me a pin. Just a pin.
2342.
I'm sorry, I did mess up. So let's stop. So 2342. Okay. No, didn't work. Try it again. So you see it's very reliable. Oh, come on. I don't have time. Okay, now it should work out. Yep, it's synchronized. We connect. $23.42. Yep, $23.42. Yep, it should have worked. So we have lots of baseband errors, but never mind, that's normal for Bluetooth. No, actually, because there is interferences. So within the handshake, there's also an algorithm for error correction, which says, whenever you don't get the packet, hop at this sequence next, I will retransmit it there. So it's really complex. It's not easy stuff. So the LMP layer, which is basically for, let's see if we captured everything here, which is for security and handshaking, we'll export it to a CVS file, which we may later import into BTCrack. So there it is. We load up the CSV file. There it is. Oh, Jesus. We missed something. A reason rewind. Do we have time to replay? Okay. So let's resynchronize. Very reliable. We have to actually remove the old pairing because it won't ask me for new pairing credentials if it's actually already authenticated. So I'll just the sniffer obviously missed the asterisk packet. Okay. So there it is. We connect. Okay. Yeah, 23, 42. Okay. I saw that coming, so I saved another capture. So I export it here. I'll launch up BTCrack. I'll import the capture, which is here. We have everything except the BD address of the master and the slave. Now what is important is that we can get it with a sniff. It's just that Frontline choose to not display it for whatever reason. So there's a nice kernel module, which happens to be known as BP105, which actually shows both. For convenience reasons, I just save them so I can copy-paste them here. So we'll paste them here and here. So, okay, there it is. So there it is. The pin is 1, 2, 3, 4, 5, 6, and the link key is this one. So it's actually not the link, the pin you gave me. I had to load a backup file because I couldn't get the pairing to work over here. But that's basically it. It's a low-powered Centrino here, so it does only 44,000 keys a second. But you'll see the problem. You get this key within 5 seconds. So now we can actually use that link key and connect to the master, pretending to be the slave, or pretend to be the master and connect to the slave. And we will be fully authenticated and have access to all services this device offers. Thanks. Okay. Yep, there it is. So what can you do with link keys? You authenticate to both devices, as I said. You can dump them from any Linux, Mac, or Windows machine. You can create an encrypted stealth channel. That's pretty awesome. You plant the link key, and you can connect to the device without that user notice, because the pairing process, we go around the pairing process as we have the link key, and you have a remote shell or a remote OBEX server, whatever you choose, over an encrypted channel without actually planting a binary or something else. You just planted the link key. So that's really tough to find, actually. How to reinforce pairing, actually checked and rule proposed to inject LMP not accepted.